Imagine Earth as a frozen marble, not just the poles, not just winter, completely frozen, ice stretching from what would one day become Antarctica to what would become the Sahara, oceans locked beneath kilometre-thick glaciers, no liquid water anywhere, the entire planet wrapped in white for 70 million years straight. This actually happened, and it lasted longer than anything you'd recognise as an ice age. Most people think of ice ages as those brief cold snaps when woolly mammoths roamed and our ancestors huddled in caves. That recent ice age, the one that ended about 12,000 years ago, lasted roughly 2.5 million years. Sounds impressive until you learn about the Huronian glaciation. 70 million years of frozen hell, starting about 2.4 billion years ago. Some estimates push it to 300 million years, though scientists argue about that upper limit. Either way, it's the longest deep freeze Earth has ever endured. Here's what makes it stranger. Life existed during this planetary ice prison. Not complex life, nothing with bones or eyes or brains. Just single-celled organisms, microbial mats clinging to existence in conditions that would make Antarctica look tropical. Most of them died. The ones that survived changed everything that came after. But we're getting ahead of ourselves. The Huronian wasn't discovered in some exotic location. It was found in 1907 near Lake Huron in Canada, hence the name. Geologists examining rock formations noticed something odd. Layers of stone that could only form under glacial conditions. Scratches on basement rocks where ice sheets had dragged boulders across them like sandpaper. Drop stones, rocks that had been frozen into icebergs, then dropped to the seafloor when the ice melted. All the signatures of glaciation, locked in stone that turned out to be incomprehensibly old. When they dated these rocks, the numbers seemed wrong. 2.4 billion years. At first, many scientists rejected it. The Earth itself was only about 4.5 billion years old at that point. How could glaciers have formed when the planet was still so young? More importantly, what could have triggered a freeze that severe, that early in Earth's history? The answer involves something that saved life on Earth and nearly destroyed it at the same time. Oxygen. Before you take your next breath, consider what that oxygen is doing to you. Right now, at the cellular level, it's stealing electrons from molecules in your body. We call this oxidation, and it's why iron rusts, why apples turn brown, why we age. Oxygen is chemically aggressive. It wants to react with everything it touches. For most of Earth's early history, there wasn't any free oxygen in the atmosphere. Life existed just fine without it, actually better than fine. The first organisms on Earth were anaerobes, creatures that not only didn't need oxygen, they found it toxic. Then, cyanobacteria evolved. These microscopic organisms developed a trick called photosynthesis, splitting water molecules to harvest energy from sunlight. The process had a waste product, oxygen. For millions of years, this oxygen didn't accumulate in the atmosphere. It immediately reacted with iron dissolved in the oceans, creating rust that settled to the seafloor in distinctive bands. We can still see these banded iron formations today, rust-coloured stripes in ancient rock, the graveyard of Earth's first oxygen. But eventually the oceans ran out of dissolved iron to oxidize. The oxygen had nowhere to go except up. It began bubbling into the atmosphere around 2.4 billion years ago. A planetary shift so profound, geologists call it the Great Oxygenation Event. Sounds positive, right? For aerobic life like us, it eventually was. For the planet's climate, it was catastrophic. The atmosphere before this event was completely different from today's. Instead of oxygen, it was rich in methane, pumped out constantly by methane-producing microbes. Methane is a greenhouse gas. Not just any greenhouse gas, one of the most powerful. It trapped heat from the sun like a thermal blanket, keeping Earth warm despite the sun being about 30% dimmer than it is today. Young stars burn cooler, and our sun was still in its youth. When oxygen flooded the atmosphere, it encountered all that methane. The two gases reacted violently. Methane oxidized into carbon dioxide and water vapor. Both are greenhouse gases too, but far weaker than methane. The thermal blanket got thin, fast. Carbon dioxide traps heat, sure. You've heard about CO2 and climate change. But compared to methane, carbon dioxide is amateur hour. Methane traps roughly 85 times more heat over a 20-year period. When Earth's methane-rich atmosphere was stripped away and replaced with carbon dioxide and water vapor, the greenhouse effect weakened dramatically. The planet's thermostat plummeted. There's another factor. The sun was dimmer. Geothermal activity, the heat from Earth's interior, was also lower than today. The planet was already cooler than it would be later in its history. Removing the methane blanket pushed it over the edge. Ice began forming at the poles. Nothing unusual about that, except the ice didn't stop. It crept toward the equator, advancing year by year, century by century. And here's where things got truly nightmarish. Ice reflects sunlight. The technical term is albedo. Fresh snow can reflect up to 90% of incoming solar radiation back into space. Dark ocean water, by contrast, absorbs most of it. As more ice formed, more sunlight was reflected. Less heat was absorbed. Temperatures dropped further, more ice formed. The feedback loop had begun. Scientists call this the ice albedo feedback, and it's one of the most terrifying mechanisms in climate science. Once it starts, it's almost impossible to stop. The ice becomes its own engine of expansion, feeding on itself, growing regardless of what triggered it initially. Earth fell into this trap around 2.4 billion years ago. The ice advanced, not slowly in geological terms. Within perhaps a few million years, glaciers reached the tropics. Rocks formed near the equator during this period show unmistakable signs of glaciation. Scratched surfaces, embedded boulders, layered sediments that could only form beneath ice sheets. The evidence is global. Canada, Michigan, Wyoming, South Africa, India, Australia. Everywhere geologists look at rocks from this era, they find ice. How cold did it get? Climate models suggest global average temperatures around -50 degrees Celsius. The equator, normally the warmest part of Earth, probably hovered around -20 degrees. About as cold as the modern poles. The entire planet had become Antarctica. Under these conditions, the oceans froze. Not completely. The deep ocean remained liquid, insulated by the ice above, but the surface locked solid. Some models suggest ice thickness reached a kilometer in places. A kilometer of ice pressing down on water that hadn't seen sunlight in millions of years. This is where the story gets strange. Life should have died. All of it. Photosynthetic organisms need sunlight, and sunlight couldn't penetrate kilometer-thick ice. Even if some light made it through cracks, the organisms would have been sealed away from the nutrients and minerals they needed. The oceans, cut off from the atmosphere, would have become anoxic, dead zones. Nothing should have survived. But something did. When scientists study rocks formed just after the Huronian glaciation ended, they find evidence of life. Not new life, not organisms that evolved from scratch. Descendants of the microbes that existed before the freeze. Somehow, impossibly, life persisted through 70 million years of planetary ice. The question of how keeps scientists awake at night. The most popular theory involves hydrothermal vents, deep underwater volcanoes that pump heat and chemicals into the ocean. Around these vents, even today, entire ecosystems thrive in complete darkness, feeding on chemical energy instead of sunlight. Perhaps colonies of microbes clustered around these hotspots, tiny oases of warmth in a frozen world. Another possibility is meltwater ponds on the ice surface, created by volcanic activity punching through the glaciers. Volcanoes didn't stop during the freeze. They kept erupting, melting holes in the ice, creating temporary pools of liquid water where sunlight could reach. Microbes might have survived in these scattered pockets, barely hanging on, waiting for conditions to improve. There's evidence for both scenarios. Neither explains everything. The truth probably involves multiple refugees, different survival strategies for different organisms. Life is stubborn. Give it the slightest crack, and it will wedge itself in. What's certain is this: the freeze didn't just test life, it changed it. The Great Oxygenation Event and the subsequent glaciation represent the first major extinction event in Earth's history. The longest one, too. Most of the anaerobic microbes that had dominated the planet for billions of years couldn't handle the combination of oxygen poisoning and extreme cold. They died in unimaginable numbers. The survivors inherited a transformed world. When the ice finally melted, which we'll get to, the planet was different. The oceans were different. The atmosphere was different. And life, having barely survived the worst Earth could throw at it, was about to explode in directions no one could have predicted. But before we get to the thaw and what came after, you need to understand something crucial. The Huronian wasn't a single event. It was at least 3 separate glaciations, possibly 4, spread across 300 million years. The planet froze, thawed, then froze again. Each time, life struggled to recover before the next freeze hit. The rocks tell this story in layers. The Ramsey Lake Formation, the oldest glacial deposits. Then a gap, representing a warm period. Then the Bruce Formation, evidence of a second freeze. Another gap. Then the Gauganda Formation, the youngest and possibly most severe glaciation. Each layer preserves a chapter of Earth's frozen history, written in stone that still exists today, waiting to be read and to be. Why did it happen multiple times? That's where the story gets complicated, where atmospheric chemistry meets plate tectonics meets sheer bad luck. Understanding these repeated freezes means understanding how Earth's climate system works at the deepest level. The first freeze, the Ramsey Lake glaciation, hit around 2.45 billion years ago. We know this because the rocks contain dropstones, boulders that were frozen into icebergs, carried far from their source, then dropped to the ocean floor when the ice melted. These stones sit embedded in fine marine sediments, completely out of place. Geological proof that ice once floated above, where now there's only rock. The ice advanced, covered the continents, pushed deep into the oceans. Then it retreated. For millions of years, Earth warmed. Not back to what it had been. The atmosphere was fundamentally different now, but warm enough for liquid water to flow freely. The sediments from this interglacial period show no sign of ice. Instead, there are carbonates, rocks formed in relatively warm, shallow seas. Life recovered. Microbes spread across the ocean floor again, building new colonies, adapting to the oxygenated world they now inhabited. Then the cold returned. The Bruce glaciation, the second freeze, arrived around 2.35 billion years ago. The geological record shows it was potentially more severe than the first. The ice sheets grew thicker. The frozen period lasted longer, and when it finally ended, the thaw was brief. Almost no time passed before the third glaciation began. The Gauganda event, possibly the worst of all. The Gauganda Formation preserves evidence of ice at low latitudes, close to the equator where sunlight hits Earth most directly. That's the smoking gun for a true snowball state. If ice existed there, it existed everywhere. The planet's reflectivity, what scientists call albedo, would have shot up. White ice reflects sunlight back into space far better than dark ocean water or land. The more ice that formed, the more sunlight bounced away. The colder it got, the more ice formed. A feedback loop with no natural break. But here's what doesn't make sense. The warm periods between glaciations. If Earth was locked in a runaway freeze, what broke it? And if conditions improved enough for liquid water to return, why did the planet freeze again? You'd expect one long, continuous ice age, not this stuttering pattern of freeze, thaw, freeze, thaw. The answer involves plate tectonics and atmospheric chemistry dancing together in ways that barely make sense, even when you understand them. During the Great Oxygenation Event, oxygen didn't just appear overnight. It accumulated in pulses. Cyanobacteria would bloom. Oxygen levels would spike. Then something would suppress them and levels would drop again. Maybe volcanic eruptions that released toxic gases. Maybe changes in ocean chemistry that limited nutrients. We don't know for certain. What we do know is that oxygen levels fluctuated wildly during this period. When oxygen was high, it scrubbed methane from the atmosphere quickly. Temperatures plunged, ice advanced. But ice covering the oceans meant cyanobacteria couldn't photosynthesize anymore. No sunlight reached them. Oxygen production stopped. Meanwhile, volcanoes kept erupting, even under the ice, pumping carbon dioxide and methane back into the atmosphere. Slowly, over millions of years, these greenhouse gases accumulated. The ice had no way to prevent it. Eventually, the greenhouse effect strengthened enough to overcome the albedo effect. The ice began to melt. With liquid water restored, cyanobacteria could photosynthesize again. Oxygen levels rose. Methane got oxidized. The cycle repeated. This explains the pattern. Earth wasn't caught in one stable frozen state. It was oscillating between two unstable conditions, both trying to assert dominance. The ice world kept trying to become permanent. The greenhouse world kept trying to break through. Neither succeeded completely for hundreds of millions of years. There's another factor, the sun itself. 2.5 billion years ago, our star was roughly 20% dimmer than today. Young stars are fainter, a well-established fact of stellar physics. This created what's called the faint young sun paradox. With less solar energy reaching Earth, the planet should have been frozen solid from the very beginning. The fact that liquid water existed for the first 2 billion years of Earth's history proves there must have been a powerful greenhouse effect, primarily from methane, keeping temperatures above freezing despite weak sunlight. When oxygen destroyed that methane blanket, Earth's climate system lost the buffer that had protected it from the sun's weakness. The planet was suddenly vulnerable to a freeze it wouldn't have experienced with a brighter star. The combination of reduced greenhouse gases and a dim sun created the perfect storm for long-term glaciation. And the ice was thick. Not just a surface coating. Models suggest glaciers reached depths of 1 kilometer in places, pressing down on the continents with unimaginable weight. The sheer mass of ice deformed the land beneath it, creating scars we can still detect in ancient rock formations. When the ice finally melted for good, the continents slowly rebounded, rising back up like a mattress after you climb out of bed. Except this process took millions of years. The evidence for these glaciations is scattered across the globe today. In Ontario, near Lake Huron, you can walk across outcrops of the Gauganda Formation and see the tillite, rocks that were ground up and mixed together by glacial action. The boulders show striations, scratches carved by ice dragging them across bedrock. In South Africa, the Maganyan Formation tells the same story from the other side of the planet. Australia has deposits. India too. Every continent preserves fragments of this frozen chapter. What's remarkable is how consistent the evidence is, despite being separated by thousands of kilometers. The magnetic signatures in these rocks, captured when the sediments formed, show they were deposited at low latitudes. The scratches on the boulders all point in directions consistent with ice flowing from the poles toward the equator. The sediment types match. Everything lines up with a global event, not regional cold snaps. Scientists didn't always believe this. When geologists first discovered glacial deposits from this era, they assumed the rocks had moved. Continental drift must have carried them from the poles to their current positions. It seemed more plausible than admitting Earth had frozen solid at the equator. But as evidence accumulated from multiple continents, all telling the same story, resistance crumbled. The planet had indeed experienced something extraordinary. The fourth possible glaciation, the Magellanic event, is the most controversial. It might be a continuation of the Gauganda, not a separate freeze. Or it could represent a final, brief return to ice after conditions had mostly stabilized. The rocks are harder to interpret, the evidence less clear. What's certain is that by 2.1 billion years ago, the pattern had stopped. The freeze-thaw cycle finally broke. Why did it end? The best explanation involves the slow but steady increase in oxygen levels. As cyanobacteria adapted to the oxygenated environment, they became more efficient. Oxygen production became more stable, less prone to the wild swings that had characterized the earlier period. With oxygen levels steadying, methane concentrations stayed low consistently. The atmosphere reached a new equilibrium. Carbon dioxide, not methane, became the dominant greenhouse gas. Volcanoes continued their work. Over millions of years, CO2 accumulated to levels high enough to maintain liquid water even with the faint sun. The balance was delicate, nothing like the thick methane blanket that had warmed early Earth, but sufficient to prevent another runaway freeze. The planet settled into a new climate regime, still cold by modern standards, but stable. The oceans changed too. During the glaciations, with ice cutting them off from atmospheric oxygen, they had become anoxic dead zones. When the ice melted, oxygen gradually penetrated the surface waters. Not deep. The interior of the oceans would remain oxygen-poor for another billion years, but enough to transform the shallow marine environment. This created new ecological opportunities for organisms that could use oxygen for metabolism. Those organisms, the survivors of the freeze, had been through hell. They'd endured oxygen poisoning and extreme cold. They'd survived in tiny refuges scattered across a frozen planet. They'd watched their world collapse and rebuild 3, possibly 4 times. Natural selection doesn't get more intense than that. Only the toughest, most adaptable lineages made it through. Those that survived were fundamentally different from their ancestors. The microbial world that emerged after the Huronian glaciation was smaller but hardier. The oxygen-intolerant anaerobes that had dominated Earth for billions of years were pushed to the margins, restricted to environments where oxygen couldn't reach. Deep ocean sediments, volcanic vents, underground aquifers. They still exist today, these ancient lineages, living fossils that remember a time before oxygen. But they would never again rule the surface world. The oxygen-using aerobes, meanwhile, inherited the planet. They spread across the ocean floor, into shallow seas, across tidal zones. Photosynthesis became the dominant energy pathway. The stage was set for everything that would follow. Eukaryotes, multicellular life, eventually us, though those developments were still unimaginably far in the future. But none of it would have happened without the freeze. The Huronian glaciation was Earth's crucible, the trial by ice that tested whether life could survive planetary catastrophe. It did, barely, and in surviving, it proved something crucial. Life on Earth wasn't fragile, it was persistent. Give it the slimmest chance, and it would cling to existence through conditions that should have been absolutely lethal. The ice tried to erase it. The ice failed. What scientists still debate is whether the Huronian qualifies as a true snowball Earth. Some argue the term should be reserved for complete global glaciation with no open water anywhere. Others use it more loosely for any ice age where glaciers reach the tropics. The evidence supports ice at low latitudes, that much is clear. Whether it covered every square meter of ocean remains uncertain. Climate models suggest it's possible for ice to reach the equator without completely freezing the planet. Even with glaciers at the tropics, there might have been a thin band of open water along the equator itself, kept liquid by the direct overhead sun. This would explain how photosynthetic life survived without requiring hydrothermal vents or meltwater pools. But the models are sensitive to assumptions. Change the albedo of ice slightly, adjust the CO2 levels a bit, and you get different results. Total freeze versus narrow equatorial ocean. Both scenarios fit some of the data. Neither fits all of it perfectly. What's not debatable is the impact. Whether the freeze was 100% complete or 95% complete doesn't change the fundamental story. Earth experienced its longest ice age. Life faced its first mass extinction. The planet's atmosphere underwent permanent transformation. And when the ice finally retreated for good, nothing was the same. The rocks remember everything. Scattered across continents today, ancient stone formations carry scars from the Huronian freeze. Geologists found the first clues in 1907 near Lake Huron, hence the name. Layers of lithified till, drop stones embedded in ancient seafloor sediments, varves marking seasonal cycles that occurred under ice sheets. The evidence was sitting there for billions of years, waiting for someone to understand what they were seeing. These aren't subtle hints. We're talking about massive geological formations spanning hundreds of kilometers. From Sault Ste. Marie to Sudbury, the Huronian supergroup tells the story in stone. 3 distinct glacial units, stacked like pages in Earth's darkest chapter. The Ramsey Lake Formation, the Bruce Formation, the Gauganda Formation. Each one represents a separate freeze, a separate near-death experience for the planet. What makes these rocks extraordinary is where else they appear. Michigan has them. Wyoming's Medicine Bow Mountains preserve similar deposits. Quebec, Nunavut, South Africa's Griquatown Basin, India, Australia. When you find the same type of glacial debris on multiple continents, all from the same time period, you're not looking at regional cold snaps. You're looking at something that affected the entire planet. The drop stones are particularly telling. These are rocks that were frozen into icebergs, carried far from their origin, then dropped into marine sediments when the ice melted. Finding them in what were tropical latitudes 2.4 billion years ago is like discovering polar bear fossils in the Sahara. It shouldn't happen unless something went catastrophically wrong with the climate. Scientists debate the exact number of freeze-thaw cycles. 3 episodes are clearly documented, possibly 4. The last one, the Magallanes glaciation around 2.2 billion years ago, might have been the worst. But here's what matters more than the count. Each time the planet froze, it had to thaw. And each time it thawed, conditions became just stable enough for life to recover before the next freeze hit. Think about that pattern for a moment. Freeze, thaw, recovery, freeze again. This went on for at least 70 million years, possibly much longer. Some estimates stretch the Huronian Ice Age to 300 million years, though that's contested. Either way, we're talking about a span of time so vast that the entire age of dinosaurs could fit inside it multiple times over. The geologic evidence paints a picture of a planet caught in feedback loops it couldn't escape. Ice reflects sunlight, cooling the planet further, creating more ice. That's the albedo effect, and during the Huronian it became a trap. Break free temporarily, and the cycle could restart with the next atmospheric shift. The planet was stuck in a pattern it couldn't resolve on its own. Between the glacial layers, there's something else. Carbonate rocks, limestone, sediments that form in warmer temperate conditions. This tells us the freezes weren't continuous. There were breaks, warm periods, relatively speaking, when the ice retreated and liquid water returned to the surface. These interglacial periods might have lasted millions of years. Long enough for life to spread again, long enough for false hope that the worst was over. Then the cold returned. The spacing between glacial events suggests they weren't random. Something was cycling in Earth's system. Volcanic activity fluctuating, atmospheric chemistry oscillating, continental positions shifting. Whatever the mechanism, it had a rhythm, and that rhythm kept bringing the ice back. Modern researchers can analyze these ancient rocks with techniques that would seem like magic to the geologists who first discovered them. Isotope ratios reveal temperature. Crystal structures indicate pressure and depth. Chemical signatures show what the atmosphere and ocean were like. Every layer is a data point, and collectively they reconstruct a climate that shouldn't have allowed life to survive. But it did survive, and the rocks tell that story too. Buried within the glacial deposits are thin layers of banded iron formations. These are chemical sediments that precipitate from seawater under specific conditions, mainly when oxygen reacts with dissolved iron. Their presence during the Huronian suggests that even under the ice, in whatever refuges life clung to, photosynthesis continued. Oxygen kept being produced. The Great Oxygenation Event didn't pause for the freeze. This is where the story becomes less about ice and more about consequences. The Huronian glaciation was triggered by oxygen, yes, but it also reinforced the oxygen revolution. By killing off the methane-producing anaerobes that kept the planet warm, the Ice Age ensured those organisms could never reclaim their dominance. The freeze was both effect and cause, locking in the atmospheric transformation that started it. The aftermath appears in the rock record as cap carbonates, thick layers of limestone and dolostone that sit directly on top of the glacial deposits. These form through a specific process. When the ice finally melted, massive amounts of CO2 that had built up in the atmosphere during the freeze dissolved into the oceans. This created carbonic acid, which weathered rocks and released calcium. That calcium combined with carbonate ions to form the distinctive layers geologists now use as markers for the end of glaciations. Cap carbonates are the signature of snowball Earth events. Their presence in the Huronian sequence is one of the strongest arguments that at least one of these freezes achieved near total ice coverage. You don't get that specific rock formation from a regular ice age. You get it from a planet emerging from a climate catastrophe. The Makanyin event left particularly dramatic evidence. Volcanic rocks called the Ongeluk Formation in South Africa were laid down right before this glaciation. Paleomagnetic analysis, measuring the ancient magnetic field preserved in the minerals, shows these rocks formed near the equator. Directly above them sit glacial deposits. Ice. At the equator. That's not a cold spell. That's a climate system in complete failure. Other researchers point to the discontinuous nature of the glacial sediments. They argue that if the planet was truly in a total freeze, we should see continuous ice deposits everywhere. Instead, we find gaps, breaks, periods where temperate sediments accumulated. This has led to alternative models like slushball Earth, where ice covered most but not all of the planet, leaving a band of open water near the equator. Climate simulations support both scenarios under different assumptions. Tweak the ice albedo slightly, and you get complete freeze. Adjust the CO2 levels, and you get partial ice coverage with equatorial oceans. The models are sensitive. Small changes in input produce dramatically different results. What everyone agrees on is the temperature. Brutal. Global averages around -50 Celsius if the freeze was complete. Even in a slushball scenario, you're looking at -20 at the equator. For comparison, modern Antarctica averages -55 in winter. The entire Huronian Earth might have been colder than the harshest place on the planet today. Under ice that thick, potentially a kilometre deep in places, the ocean would have been cut off from the atmosphere. No gas exchange, no photosynthesis in most areas. Whatever oxygen was being produced would have been minimal, trapped in isolated pockets. The deep ocean probably went anoxic again, oxygen-free zones expanding in the darkness beneath the ice. This creates a paradox. Life needs oxygen to survive in an oxygenated world, but the freeze cut off the oxygen supply. How did anything make it through? The answer lies in the exceptions. Volcanic hotspots that kept small areas ice-free. cracks in the ice where light penetrated, hydrothermal vents pumping heat and chemicals into isolated ecosystems. These weren't comfortable refuges. They were desperate last stands, tiny oases in a frozen wasteland. But they were enough. Research in modern Antarctic ice-covered lakes shows that microbial mats can survive under meters of ice, creating thin, oxygenated layers just millimeters thick through photosynthesis. If modern organisms can pull this off in extreme environments, their ancient ancestors probably could too. Evolution had already been working for over 1 billion years by the time the Huronian hit. Life had tricks. The duration is what makes it almost incomprehensible. 70 million years minimum. Think about what that means in biological terms. Entire evolutionary lineages rose and fell during the freeze. Species that adapted to ice-covered oceans had millions of years to specialize before conditions changed again. When the thaw finally came, those specialists might have gone extinct, replaced by organisms adapted to the new environment. This wasn't a single event. It was an era. The planet that entered the Huronian glaciation was fundamentally different from the one that emerged. Atmospheric composition had shifted from methane-dominated to oxygen-containing. The biosphere had been pruned of its dominant forms and repopulated by survivors. Ocean chemistry had been reset. Even the continents had moved. Continental drift slowly rearranging the map during those 70 million years of ice. When the final thaw arrived, around 2.1 billion years ago, Earth entered a new phase. The Huronian was over, but its effects would echo for the next billion years. The planet had learned, in a sense, that oxygen and ice were connected. That atmospheric chemistry could trigger climate catastrophe. That life, however resilient, existed at the mercy of planetary systems it couldn't control. The long silence that followed tells its own story. After the Huronian ended, Earth went approximately 1.5 billion years without another major ice age, the longest stretch between glaciations in the planet's history. Something had stabilized. The oxygen levels plateaued. The climate found a new equilibrium. Life expanded into the breathing room this created. But stability in Earth's history never lasts forever. That 1.5 billion year gap wasn't silence. It was preparation for something worse. Jump forward to 717 million years ago. Earth had evolved considerably since the Huronian. Eukaryotic cells now dominated. Some had learned to cooperate, forming the first multicellular organisms. The continents had merged and split multiple times. Volcanic activity pulsed through cycles. Life had diversified into forms the Huronian survivors wouldn't recognize. Then the temperature dropped. Again. The Sturtian glaciation arrived like a geological ambush. Unlike the Huronian, which built slowly through atmospheric transformation, the Sturtian had a different trigger entirely. Plate tectonics. Continental drift had positioned land masses in a configuration that choked off Earth's carbon dioxide recycling system. Volcanoes, those planetary thermostats that normally pump greenhouse gases into the atmosphere, went quiet. Not everywhere, but enough. The timing was catastrophic. Simultaneously, a massive volcanic province in what's now Canada began eroding. Sounds harmless until you understand what weathering does. Silicate rocks consume atmospheric CO2 when they break down, locking it into carbonates. This process normally balances volcanic emissions. During the Sturtian onset, the balance shattered. Volcanic output plummeted, while weathering accelerated. CO2 levels collapsed. The greenhouse effect weakened. Temperatures fell. Once they dropped below a critical threshold, around 200 parts per million of CO2, the ice albedo feedback kicked in with savage efficiency. Ice reflects sunlight. More ice means more reflection. More reflection means cooler temperatures. Cooler temperatures mean more ice. The loop became self-reinforcing, a runaway refrigeration that couldn't be stopped by anything except the one mechanism that had shut down: volcanism. The Sturtian lasted between 50 and 60 million years, shorter than the Huronian, but potentially more severe. The evidence suggests ice reached the equator. Glacial deposits from this period show up in rocks that formed near sea level in tropical latitudes. Paleomagnetic data confirms it. The magnetic signatures locked into these rocks indicate they crystallized close to the equator, yet they contain unmistakable glacial features. Dropstones, rocks carried by ice and dropped into marine sediments when the ice melted. Striations, scratches carved into bedrock by moving glaciers. Tillites, jumbled deposits left behind by retreating ice sheets. Here's what makes the Sturtian nightmare fuel. The planet stayed frozen even as volcanoes continued erupting beneath the ice. Not enough to warm things up, but enough to keep pumping CO2 into the atmosphere and ocean. Slowly, over tens of millions of years, that carbon dioxide accumulated. Building, waiting. The ice reflected so much sunlight that even rising greenhouse gas levels couldn't initially overcome the albedo effect. Earth was trapped in its own reflective prison. Climate models of this period paint an almost absurd picture. Global average temperatures around -50 Celsius. But unlike the Huronian, scientists have better constraints on the Sturtian. The models suggest that even under these extreme conditions, complete freezing might not have occurred. Something called the slushball hypothesis proposes that open water persisted near the equator, maintained by ocean currents and the slight heat from the planet's interior. This matches observations better than total freeze scenarios. The geological record shows periodic breaks in glacial deposits, layers of carbonate rock suggesting liquid water and chemical weathering. Imagine that world. Equatorial oceans barely liquid, surrounded by ice sheets kilometers thick. The temperature differential between equator and poles virtually eliminated. Weather patterns completely alien to anything Earth experiences today. Storms, if they existed, would have been bizarre. Precipitation mostly as snow. Ocean currents struggling against ice resistance. The entire hydrological cycle operating in slow motion. Life during the Sturtian had to be unbelievably tenacious. This wasn't the simple microbial world of the Huronian anymore. By 717 million years ago, organisms had evolved complex cellular machinery. Some had even figured out multicellularity. The freeze threatened to erase all that progress. Yet something survived. Multiple somethings. The refugees were probably similar to Huronian survival zones, but with a crucial difference. More diversity meant more strategies. Some organisms might have clustered around hydrothermal vents on the ocean floor, where volcanic heat created small oases of warmth and chemical energy. Others potentially survived in meltwater pools atop the ice near active volcanoes, thin films of liquid water warmed by geothermal activity. Photosynthetic organisms probably clung to existence in shallow areas where light penetrated cracks in the ice, creating those razor-thin oxygenated layers observed in modern Antarctic analogues. The Sturtian finally broke around 660 million years ago. Not through gradual warming, but catastrophically. After 57 million years of accumulation, atmospheric CO2 levels had climbed to potentially hundreds of times modern values. The greenhouse effect, suppressed for so long by ice albedo, suddenly reasserted itself with volcanic fury. The melt was rapid in geological terms, possibly just a few thousand years. Ice sheets that had endured for 50 million years vanished in a geological instant. What followed was chaos. Acid rain. Massive amounts of CO2 dissolved in precipitation, creating carbonic acid that fell on freshly exposed rock. The weathering that resulted was extreme, releasing calcium and other minerals into the ocean in vast quantities. These form the cap carbonates, distinctive layers of limestone and dolostone that sit directly atop glacial deposits worldwide. They're calling cards of snowball Earth events, proof that something extraordinary happened. The chemical signatures in these rocks tell stories of rapid environmental change, of oceans suddenly flooded with nutrients, of atmospheric chemistry swinging from one extreme to another. But the Sturtian wasn't the end. After a relatively brief warm period, maybe 10 million years, the planet froze again. The Marinoan glaciation, starting around 650 million years ago, was shorter, but equally severe. Another 15 million years of ice. The Cryogenian period, spanning both events, represents roughly 85 million years, during which Earth spent perhaps 65 million years frozen. Two separate ice ages within the same geological period, bookending a brief thaw. Why did it happen twice? The plate tectonic configuration that triggered the Sturtian didn't resolve itself quickly. Continental positions shifted gradually. Volcanic activity remained suppressed. When the Sturtian ended, the fundamental problem hadn't been fixed. The continents were still arranged to maximize weathering and minimize volcanic CO2 output. So once greenhouse gas levels dropped again after the post-Sturtian warm period, the ice returned. Familiarity breeding repetition. The Marinoan ended around 635 million years ago with another catastrophic thaw, another pulse of volcanic CO2, another super greenhouse, another layer of cap carbonates, and this time something different happened afterward. The ice didn't return. Not for hundreds of millions of years. Whatever plate tectonic configuration had caused the problem finally shifted. Volcanoes resumed normal activity levels. The carbon cycle stabilized. Earth entered a new phase. What emerged from the Cryogenian wasn't the same planet that entered it. The fossil record shows something remarkable happening shortly after the ice retreated for the final time. Around 580 million years ago, roughly 55 million years after the Marinoan ended, complex life exploded across Earth's oceans. The Ediacaran fauna, strange quilted organisms unlike anything alive today, fronds anchored to the seafloor, circular forms with radial symmetry, creatures that don't fit neatly into modern taxonomic categories. This was followed by something even more dramatic, the Cambrian explosion beginning around 540 million years ago. Within just 20 million years, every major animal body plan appeared in the fossil record. Eyes evolved, shells formed, predation became widespread. The ecology of Earth's oceans transformed from simple to complex, almost overnight in geological terms. Scientists still debate the connection between the Cryogenian glaciations and this burst of evolutionary innovation. Did the ice ages cause the explosion? Several mechanisms seem plausible. The freeze might have created a genetic bottleneck, killing off most lineages and leaving the survivors with empty ecological niches to fill. Massive glacial erosion during the ice ages would have ground continents to dust, releasing nutrients that washed into post-glacial oceans. This nutrient surge could have fueled unprecedented biological productivity. There's also the calcium hypothesis. Research suggests volcanically active mid-ocean ridges during the Cryogenian caused a massive surge in ocean calcium concentrations. This made skeleton and shell formation suddenly viable. Hard body parts enabled new lifestyles, new defenses, new predatory strategies. The fossil record explodes precisely because organisms could finally leave hard remains instead of just soft impressions. But here's what really stands out. The Cryogenian represents the last time Earth experienced glaciation on that scale. Sure, ice ages have returned. The planet's been cold many times since. But nothing matching the severity or duration of those Cryogenian freezes. Something changed fundamentally. Part of it was life itself. By the end of the Cryogenian, organisms had diversified to the point where they influenced global chemistry. Photosynthetic organisms pumped oxygen. Animals stirred sediments, affecting nutrient cycles. The biosphere became a climate regulator, not just a passive victim of climate change. This feedback loop, biology influencing, chemistry influencing, climate influencing biology, created stability the early Earth lacked. Plate tectonics also played a role. After the Cryogenian, continental configurations never again aligned quite so perfectly for catastrophe. Volcanic activity maintained more consistent levels. The carbon cycle found a rhythm that, while not unchanging, avoided the extremes that triggered snowball conditions. Earth learned balance, though not permanently. The Andean-Saharan Ice Age hit around 450 million years ago, significant, but regional rather than global. Ice sheets formed over what's now Africa and South America, then positioned near the South Pole, cold but not catastrophic. Life by this point was diverse enough and adaptable enough to weather it without mass extinction. The freeze came and went without fundamentally reshaping the planet. Then the Karoo Ice Age, roughly 300 million years ago. Again, primarily affecting southern hemisphere landmasses clustered near the pole. Glaciers advanced and retreated. Sea levels fluctuated, but the equator stayed warm. Ocean currents continued flowing. Life endured, even thrived in some areas. These were ice ages in the traditional sense, cyclic climate variations rather than planetary emergencies. What made the Huronian and Cryogenian different wasn't just their severity, it was their totality. They represented system failures, moments when Earth's regulatory mechanisms broke down completely. The planet had to find new equilibrium states through brute force. Freeze everything until volcanic CO2 built up enough to force a thaw. Then reset. Modern ice ages, including the Quaternary we're technically still in, operate on different principles. Orbital variations drive climate cycles. Ice sheets grow and shrink over tens of thousands of years, not millions. The planet has learned, in a sense, how to have ice ages without catastrophe. Glaciers advance from the poles. They never reach the tropics. Life adapts to the cycles rather than barely surviving them. The difference is regulation. Multiple feedback systems now keep climate within bounds. Ocean circulation distributes heat. Atmospheric chemistry responds to biological activity. Continental positions allow sufficient volcanic outgassing. The carbon cycle operates fast enough to prevent runaway cooling. These weren't features of early Earth. They developed through billions of years of planetary evolution. Stand on the shore of Lake Huron today. Look at the rocks. They remember being ground beneath glaciers during the longest ice age Earth has ever known. They contain stories of a planet that nearly gave up on liquid water entirely, of life that survived in refuges so marginal they barely qualified as habitable, of an atmosphere that betrayed the organisms it later sustained. Those rocks also remember the thaw, the slow return of warmth, the expansion of life into empty oceans, the billion years of relative stability that followed. They're monuments to resilience, both planetary and biological. The Huronian taught Earth a brutal lesson about atmospheric chemistry. Mess with greenhouse gas ratios, face the consequences. The Cryogenian reinforced it with compound interest. Two separate freezes, each lasting tens of millions of years. By the time those ended, the planet had figured out systems to prevent repetition. Not perfectly. Ice ages still happen, but nothing like those ancient catastrophes. What comes next in Earth's climate story involves shorter timescales but no less drama. The ice would return, again and again, but never quite so completely. The Quaternary Ice Age doesn't fit the pattern you'd expect. It started 2.6 million years ago. It's still happening. Right now, this moment. We're living inside an ice age, specifically a warmer phase called an interglacial. The glaciers haven't disappeared. They've just retreated to Greenland and Antarctica, waiting. This changes how you think about climate, the normal state we experience. the one with farms and cities and moderate weather, isn't normal at all. It's a brief, warm interval in an ongoing freeze cycle. The ice will return, not if, when. Understanding this requires abandoning the idea of ice ages as discrete events. The Quaternary operates differently. It's a climate oscillation, swinging between glacial periods when ice sheets cover Canada and northern Europe, and interglacials like now, when they pull back. The whole cycle repeats roughly every 100,000 years. We're about 12,000 years into the current interglacial. Comfortable, but temporary. The mechanics behind these cycles stumped scientists for decades. Why would ice advance and retreat with such regularity? The answer turned out to be astronomical, not geological. Earth's orbit isn't stable. It wobbles, tilts, and stretches over tens of thousands of years. These variations, called Milankovitch cycles after the Serbian scientist who calculated them, change how much sunlight hits different parts of the planet. When Earth's tilt decreases, northern summers get cooler. Snow that falls in winter doesn't fully melt. It accumulates. Year after year, the buildup grows. Eventually, you have ice sheets kilometers thick spreading south from the Arctic. The opposite happens when orbital parameters favor stronger summers. Ice melts faster than snow accumulates. Glaciers retreat. Simple physics driving massive planetary changes. But orbital variations alone can't explain the magnitude of the shifts. They're the trigger, not the whole story. What amplifies the effect is feedback. As ice sheets grow, they reflect more sunlight back to space. Surface temperatures drop further. More ice forms. The cycle reinforces itself until something breaks the pattern. Carbon dioxide plays a crucial role here, though differently than in the ancient ice ages. During glacial periods, atmospheric CO2 drops to around 180 parts per million. During interglacials, it rises to about 280. The ocean acts as a massive carbon reservoir, absorbing more when cold and releasing it when warm. This creates a feedback loop that magnifies the orbital forcing. The result? Temperature swings of 5 to 10 degrees Celsius globally, massive ice sheets advancing and retreating, sea levels rising and falling by 120 meters, all driven by orbital wobbles you'd need precision instruments to detect directly. The evidence for these cycles is preserved in ice. Antarctic ice cores contain trapped air bubbles dating back 800,000 years. Each layer records atmospheric composition and temperature at the time the snow fell. Scientists can literally read climate history year by year, buried in frozen time. The pattern that emerges is striking. Glacial periods last roughly 90,000 years. Interglacials about 10,000. The transitions between them are rapid, geologically speaking. A few thousand years to shift from full glacial to warm interglacial. Then a long, slow slide back into ice. We're living in one of the short, warm periods. The last glacial maximum peaked 20,000 years ago. Ice sheets covered Canada, northern Europe, and parts of Asia. So much water was locked in ice that sea levels dropped 120 meters below present. You could walk from France to England. Indonesia and Australia were connected by land bridges. The geography was unrecognizable. Then the thaw began. Between 20,000 and 10,000 years ago, Earth underwent dramatic warming. The ice sheets melted. Sea levels rose. Coastlines drowned. Entire ecosystems shifted latitude as temperatures climbed. This wasn't gradual. Periods of rapid change punctuated the transition. The Younger Dryas, a brief return to glacial conditions 12,000 years ago, demonstrated how quickly climate could reverse. Humans experienced all of this. Our species evolved during the Quaternary Ice Age. We survived multiple glacial cycles. When ice covered the north, humans lived in refugia, pockets of habitable land in southern Europe, Africa, and Asia. When the ice retreated, populations expanded, following herds northward into newly exposed territory. the cycles shaped human evolution in profound ways. Rapid climate shifts favored adaptability over specialization. Groups that could adjust quickly to changing conditions survived. Those locked into specific environments didn't. This selective pressure may have contributed to the development of our species' remarkable behavioral flexibility. Agriculture emerged during the current interglacial, not coincidentally. Stable climate allowed humans to settle, domesticate crops, and build permanent structures. The entire edifice of civilization rests on 10,000 years of unusual climate stability. Before that, conditions changed too rapidly and unpredictably for complex societies to develop. But here's what most people miss. The current interglacial is already unusually long by quaternary standards. Previous warm periods lasted 10,000 to 15,000 years before sliding back into glaciation. We're at 12,000 years and counting. Orbital parameters suggest we should be cooling. Ice sheets should be advancing. They're not. For reasons we'll explore later, the Quaternary differs from ancient ice ages in scale and mechanism. The Huronian and Cryogenian were catastrophic system failures. The planet lost control of its climate entirely. The Quaternary is more like a climate thermostat cycling between set points. Extreme, but regulated. The ice never reaches the tropics. Ocean circulation continues. Life doesn't face extinction. These are ice ages Earth has learned to manage without existential crisis. What drives the Quaternary's overall existence? Why did this pattern of glacial cycles begin 2.6 million years ago and not earlier? The answer involves plate tectonics and atmospheric chemistry in combination. Around 3 million years ago, the Isthmus of Panama formed, connecting North and South America. This closed the seaway between the Atlantic and Pacific. Ocean circulation patterns changed fundamentally. The Gulf Stream strengthened, carrying more warm water north. This increased snowfall in the Arctic, allowing ice sheets to grow. Simultaneously, atmospheric CO2 levels had been declining for millions of years. Not catastrophically like during the Huronian, but steadily. Lower greenhouse gas concentrations made the planet more sensitive to orbital variations. When Milankovitch cycles pushed toward cooler conditions, ice could actually accumulate rather than melting each summer. The combination created conditions for cyclic glaciation. Change the ocean circulation, lower the CO2, and suddenly orbital wobbles matter. Before these changes, similar orbital variations occurred without triggering ice ages. The planet was too warm. After these changes, the oscillations began. But the Quaternary's glacial cycles aren't perfectly regular. The dominant rhythm is 100,000 years, matching Earth's orbital eccentricity cycle. But earlier in the Quaternary, the pattern was different. Between 2.6 and 1 million years ago, glacial cycles occurred every 41,000 years, matching the obliquity cycle. Something changed a million years ago. The cycles lengthened and intensified. Scientists call this the mid-Pleistocene transition. The mechanism behind it remains debated. Perhaps ice sheets grew large enough to affect their own dynamics. Perhaps atmospheric CO2 levels crossed some threshold. The shift happened, and glacial periods became longer and more severe. This matters because it demonstrates that even within a single ice age, the behavior evolves. The Quaternary isn't static. It's a dynamic system responding to multiple feedbacks. Understanding why cycles changed helps predict what might happen next. During glacial maxima, ice sheets weren't uniform. They advanced faster in some regions than others. The Laurentide ice sheet covered Canada and the northern United States. The Fennoscandian ice sheet buried Scandinavia and northern Europe. Smaller ice caps formed in the Andes, Alps, and Himalayas. Each had distinct dynamics driven by local conditions. The Laurentide was particularly massive. At its peak, it contained enough ice to lower global sea level by 80 meters on its own. The weight of the ice pressed down on the continent, depressing the crust by hundreds of meters. When the ice melted, the land slowly rebounded. Parts of Canada are still rising today, recovering from the load of ice removed 10,000 years ago. This glacial rebound creates measurable effects. Coastlines shift, rivers change course. Ancient beaches now sit hundreds of meters inland, high above current sea level. The Earth's crust is still adjusting to the removal of those ice sheets, a process that will continue for thousands more years. The melting itself released catastrophic amounts of water. Lake Agassiz, formed by glacial meltwater in North America, was larger than all the Great Lakes combined. When ice dams holding it back failed, the lake drained in massive floods. Torrents of fresh water poured into the ocean, potentially disrupting ocean circulation and triggering rapid climate shifts. These meltwater pulses show up in ocean sediment cores as sudden changes in salinity and temperature. They mark moments when the climate system lurched rather than transitioned smoothly. The younger Dryas cold period may have been triggered by one such pulse, dumping so much fresh water into the North Atlantic that it shut down the Gulf Stream temporarily. Climate during glacial periods wasn't uniformly cold. Regional patterns created habitable zones, even at the height of ice sheet advance. Southern Europe remained relatively mild. Parts of Asia experienced cold but dry conditions. Tropical regions cooled but stayed wet. Humans and animals found refuge in these areas, waiting for the ice to retreat. The transitions between glacial and interglacial created opportunities. As ice melted and ecosystems shifted, new ecological niches opened. Species that could migrate quickly and adapt to changing conditions thrived. Those that couldn't faced extinction. The Quaternary's rapid climate oscillations drove evolutionary change through constant environmental pressure, which brings us to the present situation. We're in an interglacial that by all measures should be ending. Orbital parameters favor cooling. Ice sheets should be advancing from the Arctic. The Milankovitch cycles that drove previous glaciations are pushing in that direction. Instead, the planet is warming, rapidly. The glacial cycle that dominated the past 2.6 million years appears to have been interrupted. Something unprecedented in the Quaternary record is happening. The Ice Age continues technically, but its rhythm has broken. Understanding what comes next requires examining not just natural climate drivers, but a new factor. One that emerged only in the most recent geological instant. Human influence on atmospheric chemistry now rivals the processes that ended ancient snowball Earths. We've become a geological force capable of altering planetary climate faster than orbital variations ever could. The Quaternary Ice Age isn't over, but its future has become radically uncertain. The driver isn't orbital mechanics anymore. It's carbon dioxide released from burning fossil fuels, and the speed of that change makes Milankovitch cycles look glacial by comparison. Consider what's happening. Atmospheric CO2 concentration has risen from 280 parts per million before industrialization to over 420 today. That increase occurred in roughly 200 years. During the transition from the last glacial maximum to our current interglacial, CO2 rose by about the same amount. That natural increase took 10,000 years. We've replicated it 50 times faster. The warming is global but uneven. Arctic temperatures have risen twice as fast as the global average. Sea ice extent has declined dramatically. The Greenland and Antarctic ice sheets are losing mass at accelerating rates. Glaciers worldwide are retreating at speeds unprecedented in the instrumental record. This isn't speculation, it's measurement. Satellites track ice sheet mass balance. Tide gauges record sea level rise. Weather stations document temperature trends. The data converges on the same conclusion. The planet is warming, and human activity is the dominant cause. But here's what makes this truly remarkable from a geological perspective. We're watching something that usually takes millennia happen within a single human lifetime. The climate system is being forced into a state it hasn't experienced in millions of years. Not thousands, millions. The last time atmospheric CO2 was this high. During the Pliocene epoch 3 million years ago, sea levels were 15 to 25 meters higher than today. Forests grew in the Arctic. The climate system eventually equilibrated to those CO2 levels. But it took thousands of years for ice sheets to fully respond. We're creating Pliocene atmospheric chemistry on a timescale measured in decades. This creates a dangerous lag. Ice sheets don't melt overnight. Ocean circulation doesn't reorganize instantly. These systems have inertia. They respond slowly to forcing, but once they start changing, they can cross thresholds that accelerate the process. Take the Greenland ice sheet. It contains enough ice to raise global sea level by 7 meters. Current warming has pushed temperatures in Greenland beyond the range that sustained the ice sheet for thousands of years. Even if we stopped all emissions tomorrow, the ice sheet would continue shrinking for centuries, committed to its trajectory by the warming already locked in. The same logic applies to other tipping points in the climate system. The Amazon rainforest, which generates much of its own rainfall, faces drying that could flip it to savanna. The West Antarctic ice sheet, grounded below sea level, becomes vulnerable to irreversible collapse if warm ocean water penetrates beneath it. Permafrost, frozen ground containing massive amounts of organic carbon, thaws and releases methane and CO2, amplifying warming. These aren't hypothetical scenarios. They're processes already underway, visible in satellite data and field observations. The question isn't whether these changes will happen. It's how fast, and whether they'll cascade into something beyond our ability to predict or control. Which brings us back to the ice ages. Understanding how climate changed in the past provides context for what's happening now. It reveals the sensitivity of the climate system to atmospheric composition. It shows how feedback loops can amplify small changes into massive reorganizations. It demonstrates that the Earth's climate has multiple stable states, and that transitions between them can be abrupt. The geological record contains warnings. During the Paleocene-Eocene thermal maximum 56 million years ago, massive carbon release triggered rapid warming. Global temperatures rose by 5 to 8 degrees Celsius in less than 20,000 years. The ocean acidified. Species went extinct. It took the Earth 200,000 years to recover. We're injecting carbon into the atmosphere faster than during the PETM. Much faster. The rate of change, not just the magnitude, determines how ecosystems and ice sheets respond. Rapid change overwhelms adaptation. Species can't migrate quickly enough. Ice sheets can't adjust gradually. The system lurches rather than transitions smoothly. But there's a crucial difference between past climate changes and what's happening now. Previous warmings, even rapid ones by geological standards, occurred over thousands of years. That gave some species time to shift their ranges, some ecosystems time to reorganize. We're compressing that timescale by orders of magnitude. The Quaternary Ice Age taught us that climate is sensitive. Small changes in orbital parameters triggered massive ice sheet growth and collapse. The Huronian glaciation showed us that atmospheric chemistry controls planetary temperature. The Cryogenian snowball episodes demonstrated that feedback loops can lock the climate into extreme states for millions of years. Now we're running an experiment. We're altering atmospheric composition at a rate the Earth hasn't experienced since the asteroid impact that ended the Cretaceous. We're testing the climate system's response to forcing more rapid than anything in the ice core record, and we're doing it without knowing exactly where the thresholds are. How much warming triggers irreversible ice sheet collapse? At what point does the Amazon rainforest transition to savanna? When do ocean currents reorganize? These questions don't have precise answers because the Earth has never been in exactly this configuration before. The ice ages provide analogues, but they're imperfect. Past warmings occurred with different continental configurations, different ocean circulations, different biospheres. The Pliocene had high CO2, but it reached that level over millions of years, not centuries. The PETM involved carbon release, but from volcanic sources operating on geological timescales. What's happening now is genuinely unprecedented, not just in human history, in Earth history. Consider the speed. During deglaciation, ice sheets retreated at rates of tens of meters per year. Today, some glaciers are thinning at rates of meters per year across their entire extent. The Greenland ice sheet is losing roughly 280 billion tons of ice annually. Antarctica is losing about 150 billion tons per year. These numbers fluctuate, but the trend is clear and accelerating. Sea level rose about 120 meters as the last ice age ended. That occurred over roughly 10,000 years, an average of 1.2 centimeters per year. Current sea level rise exceeds 3 millimeters per year and is accelerating. That might not sound like much, but it's already faster than at most times during deglaciation, and we're still in the early stages of ice sheet response. The ocean is absorbing most of the excess heat. More than 90% of the energy trapped by greenhouse gases goes into warming seawater. This has delayed atmospheric warming, but it's changing ocean chemistry and threatening marine ecosystems. The ocean has also absorbed about a quarter of the CO2 we've emitted, slowing atmospheric buildup, but acidifying seawater at rates not seen in millions of years. These processes create commitments. Even if emissions stopped today, the ocean would continue warming for decades, as heat already absorbed at the surface mixes into deeper layers. Ice sheets would continue shrinking for centuries, responding to temperatures already achieved. The climate wouldn't stabilize quickly. It would continue changing, coasting on momentum we've already created. But emissions aren't stopping. They're still rising. Each year, we add roughly 40 billion tons of CO2 to the atmosphere. That's about 100 times faster than volcanic emissions, the main natural source. We've become a geological force comparable to volcanism, but operating on human rather than geological timescales. This creates a profound asymmetry. We can change the climate rapidly through emissions, but we can't reverse it quickly by stopping. Carbon dioxide persists in the atmosphere for centuries. Some fraction remains for thousands of years. The warming we've caused will outlast our civilization. The sea level rise we've initiated will continue for millennia. The ice ages show us that climate has changed dramatically before. The quaternary oscillations prove the system is sensitive. The snowball episodes demonstrate it can reach extreme states. But those changes, even the rapid ones, unfolded over timescales that allowed some adaptation. We're testing whether the biosphere can adapt to change measured in decades. We're discovering whether human civilization, built during an unusually stable climate, can function as that stability dissolves. The geological perspective reveals both the scale of what's happening and the difficulty of stopping it. Climate operates on momentum. Ice sheets, oceans, and ecosystems don't respond instantly to forcing. They adjust gradually, with lags and feedbacks that can persist for millennia. This means the climate of 2100 isn't determined just by what we do between now and then. It's influenced by emissions from decades ago that are still working through the system. And our current emissions commit us to changes that will unfold long after we've stopped burning fossil fuels. Understanding ice ages helps us grasp these timescales. It provides context for the inertia in the climate system. It shows how long it takes for ice sheets to grow and shrink, for ocean circulation to reorganize, for ecosystems to shift. These processes operated during past climate changes, and they're operating now. But we've accelerated the forcing beyond anything in their evolutionary history. The question facing us isn't whether we're changing the climate. The evidence for that is overwhelming. The question is whether we can slow the change enough for adaptation to occur, whether natural or engineered, and whether we can avoid crossing thresholds that would commit us to changes beyond our ability to manage. The ice ages ended through natural processes. orbital variations that shifted solar heating patterns. Those processes continue today, but they're overwhelmed by anthropogenic forcing. We've become the dominant driver of climate change. That gives us responsibility, but also agency. Unlike the ice sheets of the Pleistocene, which advanced and retreated according to astronomical cycles, we can choose how much we warm the planet. That choice exists because of timing. If we'd started reducing emissions decades ago when the science became clear, we'd have far more options now. The delay has narrowed our path. Each year we wait. The required reductions become steeper, the costs higher, the disruptions more severe. But the choice remains. The climate system responds to forcing. Reduce the forcing, and you reduce the warming. The lag means we can't stop warming immediately, but we can limit how far it goes. This brings us to a darker question. What happens if we don't limit it? What happens if forcing continues to increase? The ice ages provide some unsettling answers. They show us that Earth has stable states. Glacial periods persisted for tens of thousands of years. Interglacials lasted shorter spans. The planet settled into these configurations and remained there until something pushed it out. We're now pushing the system toward a state it hasn't occupied in millions of years. A world warmer than any interglacial of the Quaternary, warmer than the Pliocene, when sea levels were 15 meters higher, potentially warmer than the early Eocene, 50 million years ago, when palm trees grew in Alaska and crocodiles swam in the Arctic. Those weren't brief excursions. They were stable climates that persisted for millions of years. The planet adjusted to them. Ice sheets retreated or vanished. Ocean circulation reorganized. Ecosystems migrated to new latitudes. Carbon cycled through different pathways. The Earth system found equilibrium at those temperatures and remained there. We're not aiming for those climates deliberately, but we're applying forcing that could take us there. The question is whether we'll stop before we cross thresholds that commit us to those outcomes, and whether those thresholds are gradual slopes we can reverse, or cliffs we'll tumble over without warning. The paleoclimate record suggests both exist. Some transitions during ice ages were smooth. The climate warmed gradually as CO2 rose. Ice sheets retreated steadily. Sea levels climbed predictably. Other transitions were abrupt. Ice sheets collapsed in pulses. Ocean currents reorganized within decades. Regional climates flipped between states so quickly that ecosystems couldn't adapt. The difference often came down to feedbacks. Systems with strong negative feedbacks resist change, push them, and they push back, dampening the response. Systems with strong positive feedbacks amplify change. A small push triggers a larger response, which triggers an even larger response, cascading until something breaks or a new equilibrium is reached. Ice sheets contain both. Negative feedback stabilize them. As a glacier advances, it reaches lower elevations where temperatures are warmer, slowing further growth. As it retreats, it moves to higher elevations where temperatures are colder, slowing further melting. This feedback kept ice sheets relatively stable during much of the Quaternary. But positive feedbacks destabilize them. The ice albedo effect amplifies both growth and retreat. Surface melting creates meltwater that lubricates the base, accelerating flow toward the ocean. Ice shelves that buttress the sheet can collapse suddenly, unleashing faster discharge. Marine-based ice sheets sitting on bedrock below sea level face a particularly nasty feedback. As they retreat, the ice front moves into deeper water, where more of the ice is in contact with warming ocean. This accelerates melting, driving further retreat into even deeper water. West Antarctica sits in this configuration right now. So does part of Greenland. Both are losing mass. The question is whether that loss will remain gradual, allowing time for adaptation, or whether it will accelerate into irreversible collapse. The paleoclimate record shows that ice sheets can collapse. During the last deglaciation, massive ice shelves disintegrated within centuries. The Laurentide ice sheet, which covered Canada and parts of the northern United States, vanished in less than 10,000 years. That's geologically instantaneous. Meltwater pulses from its collapse raised global sea level by meters in spans shorter than a human lifetime. Those collapses were driven by orbital forcing and rising CO2. The mechanisms at play then are operating now, but we're applying forcing faster than at any point during that transition. We're testing whether modern ice sheets will respond gradually or catastrophically. Ocean circulation faces similar thresholds. The Atlantic meridional overturning circulation, which includes the Gulf Stream, operates as a conveyor belt. Warm surface water flows north, cools, becomes dense, sinks, and returns south at depth. This circulation transports heat from the tropics toward the poles, moderating climate in the North Atlantic region. During the last ice age, this circulation shut down repeatedly. Each shutdown plunged Europe and North America into severe cold within decades. Each restart brought rapid warming. The transitions were so abrupt that they appear in ice cores and sediment records as sharp boundaries. Ecosystems didn't adapt, they were replaced. The shutdowns were triggered by freshwater flooding the North Atlantic. Meltwater from retreating ice sheets diluted the surface ocean, reducing its density. Without dense water to sink and drive the circulation, the conveyor stalled. We're now adding fresh water to the North Atlantic again. Greenland is melting. Arctic sea ice is disappearing. Increased precipitation in high latitudes is altering salinity. The circulation has already slowed by about 15% since the mid-20th century. Models disagree on whether it will shut down entirely. Some suggest gradual weakening. Others show potential for abrupt collapse if freshwater input crosses a threshold. We don't know where that threshold lies or how close we are to it. This uncertainty characterizes many climate thresholds. We know they exist because the paleoclimate record shows the system crossing them. We don't always know what triggers them, where they sit relative to current conditions, or how fast the transition occurs once they're crossed. That makes them difficult to manage. If you knew exactly where the edge of a cliff was, you could stop safely before reaching it. If you only knew the cliff existed somewhere ahead in the fog, you'd need to proceed far more cautiously. We're walking into that fog. The ice ages show us that cliffs exist. Abrupt transitions, tipping points, thresholds beyond which change becomes self-sustaining. They're embedded in the physics of the climate system. Ice albedo feedbacks, ocean circulation, permafrost carbon, methane hydrates. Each represents a potential amplifier that could accelerate warming beyond what our emissions alone would cause. Some of these feedbacks are already active. Arctic permafrost is thawing, releasing carbon dioxide and methane that have been frozen for millennia. The emissions are still small compared to fossil fuel burning, but they're growing. Models project they could contribute to the equivalent of several decades of current emissions over the next century. That's carbon we haven't accounted for in our reduction targets. It's forcing we've triggered but can't easily turn off. Methane hydrates, frozen deposits of methane on the seafloor and in permafrost, represent another potential feedback. Warming could destabilize these deposits, releasing methane into the atmosphere. Methane is a potent greenhouse gas, though it breaks down faster than CO2. Large releases could cause rapid warming pulses. The paleoclimate record shows evidence of methane release events during past warming periods, though the exact mechanisms and magnitudes remain debated. These feedbacks introduce nonlinearity into the climate response. Warming doesn't necessarily scale smoothly with forcing. Small additional warming could trigger large additional feedbacks. This makes prediction difficult. It also makes the stakes higher. If we're approaching thresholds, we won't necessarily know until we've crossed them. And once crossed, they may be difficult or impossible to reverse. The ice ages demonstrate this hysteresis. The climate required certain conditions to enter glaciation, but different conditions to exit it. The system has memory. Its future state depends not just on current conditions, but on how it got there. This complicates our path forward. Stabilizing the climate isn't as simple as stabilizing CO2 concentrations. Even if we hold forcing constant, the Earth system will continue adjusting for centuries as ice sheets, oceans, and ecosystems catch up to the forcing already applied. And if we've triggered feedbacks, those will continue operating regardless of what we do with emissions. This doesn't mean action is futile. It means timing matters enormously. The faster we reduce emissions, the less warming we commit to, and the lower the chance of triggering irreversible feedbacks. Every 1/10 of a degree, we prevent matters because it reduces the probability of crossing thresholds we can't uncross. The choice isn't between climate change and no climate change. That choice ended when we started burning fossil fuels at scale. The choice now is between manageable climate change and catastrophic climate change. Between a world that's warmer but recognizable and a world transformed beyond our ability to adapt. The ice ages show that both futures are physically possible. Earth has been much warmer and much colder than today. It's survived both. But survival of the planet isn't the question. The question is survival of complex human civilization in the narrow climate band we've built it for. We've constructed our entire infrastructure, agriculture, and settlement patterns around the climate of the Holocene. Coastal cities assume sea levels will remain roughly stable. Agricultural systems assume rainfall patterns, and growing seasons will remain predictable. Water resources assume snowpack and glacier melt will continue feeding rivers. These assumptions are already breaking down. We're seeing the early stages of what happens when climate stops behaving as expected. Droughts lasting longer than historical records. Floods exceeding design specifications of infrastructure. Heat waves pushing beyond the tolerance of crops and human physiology. These aren't anomalies. They're the new baseline, and it's going to keep shifting. The ice ages teach us that climate is never truly stable. Even during the long glacial periods, it fluctuated. Even during interglacials, it varied. What made the Holocene special wasn't perfect stability, but sufficient stability for agriculture to develop and civilization to flourish. We're losing that. The rate of change now exceeds anything in the Holocene. It exceeds anything in the last several thousand years. It approaches rates seen during the most abrupt transitions of the last ice age, events that collapsed ecosystems and reorganized the biosphere. But those events occurred in a world with far fewer humans, no global infrastructure, and ecosystems that hadn't been fragmented by development. We're conducting this experiment in a world with 8 billion people, cities housing tens of millions, agriculture feeding populations dependent on global supply chains, and ecosystems already stressed by habitat loss and pollution. The buffer that allowed adaptation during past climate changes has largely disappeared. This amplifies the risk. A climate shift that would have been survivable 10,000 years ago could be catastrophic now. Not because the shift is necessarily larger, but because our capacity to absorb it is smaller. We've optimized for efficiency rather than resilience, creating systems that work brilliantly under stable conditions, but fail catastrophically when those conditions change. The ice ages also reveal how long climate change persists. Even after forcing stops, the system continues evolving. Ice sheets take millennia to fully adjust to new temperatures. Ocean heat content takes centuries to equilibrate. Ecosystems require generations to migrate and adapt. We're not just altering the climate for our lifetime. We're altering it for timescales that dwarf human history. The CO2 we're emitting today will influence climate for thousands of years. Some fraction will remain in the atmosphere for tens of thousands of years. The warming we're causing will persist even after we've transitioned entirely to renewable energy. even after we've stopped adding greenhouse gases to the atmosphere. This permanence is difficult to grasp. We're used to problems that can be solved, where action produces results within observable timeframes. Climate change operates differently. The benefits of reducing emissions won't be felt immediately. They'll accumulate slowly, preventing warming that would otherwise have occurred decades or centuries from now. That makes it politically challenging. The costs of action are immediate and visible. The benefits are distant and counterfactual. We're asking societies to make sacrifices now to prevent outcomes that won't fully manifest for generations. Yet that's exactly what the science demands. The ice ages show that once certain thresholds are crossed, reversal becomes extraordinarily difficult. It's far easier to prevent ice sheet collapse than to regrow an ice sheet. Far easier to maintain ocean circulation than to restart it after shutdown. Far easier to keep permafrost frozen than to refreeze it after thaw. Prevention operates on fundamentally different logic than repair. That asymmetry defines our situation. The climate system doesn't care about fairness or human timescales or political cycles. It responds to physics. Energy balance, heat content, greenhouse gas concentrations. These variables move according to laws that predate civilization and will outlast it. Consider what happens when we stop emitting CO2 entirely. Not reduce, stop. Complete cessation tomorrow. The warming doesn't stop. It continues for decades as the ocean absorbs heat already in the atmosphere. Sea level keeps rising for centuries as ice sheets adjust to temperatures already realized. Some fraction of that CO2 remains airborne for millennia, continuing to trap heat long after the last fossil fuel plant shuts down. This persistence creates a moral dimension that's uncomfortable to confront. We're not just affecting our generation, we're altering the conditions under which dozens of future generations will live. The choices we make in the next few decades will shape climate for longer than recorded history extends backward. Ice ages reveal the magnitude of change possible within Earth's climate system. They show what happens when feedback loops align, when thresholds are crossed, when the planet shifts from one stable state toward another. The most extreme example sits deep in Earth's past. Over 2 billion years ago, during the Huronian glaciation, the planet froze for roughly 70 million years. 70 million years. That's longer than the entire reign of dinosaurs. Longer than the time since their extinction. An ice age so prolonged, it's difficult to conceptualize. What caused it? Oxygen. Early photosynthetic organisms began producing oxygen as waste. It accumulated slowly at first, absorbed by iron dissolved in the oceans, creating the banded iron formations still visible in ancient rocks. But eventually, the oxygen saturated those sinks and began building up in the atmosphere. Methane dominated the early atmosphere, a far more potent greenhouse gas than CO2. When oxygen levels rose, it reacted with that methane, converting it to CO2 and water. Both are greenhouse gases, but much weaker than methane. The greenhouse effect collapsed. Temperatures plummeted. The planet froze. Not just the poles. Evidence suggests ice reached the equator. A snowball Earth scenario where glaciers covered virtually every landmass and sea ice locked the oceans. For 70 million years, life survived somehow, probably in refugia near volcanic vents or beneath sea ice, where sunlight could still penetrate. But the biosphere that existed before the freeze was largely annihilated. When the ice finally retreated, it left behind a planet transformed, both in climate and in the forms of life that had endured. What ended it? Volcanoes. They continued erupting beneath the ice, releasing CO2 into the atmosphere. Normally, weathering of rocks would remove that CO2. But with the continents buried under glaciers, weathering essentially stopped. CO2 accumulated unchecked for millions of years until it reached concentrations high enough to overcome the ice albedo feedback and trigger warming. The thaw when it came, was catastrophic. The planet lurched from icehouse to hothouse in geological instants. Temperatures soared. The ice sheets collapsed. Meltwater floods carved through landscapes. This wasn't the only time Earth experienced snowball conditions. The Cryogenian period, roughly 700 million years ago, saw at least 2 global glaciations. The Sturtian glaciation lasted 50 to 60 million years. The Marinoan that followed persisted for another 15 million. Both ended the same way. Volcanic CO2 accumulation, runaway warming, sudden collapse of ice cover. These events left distinctive signatures in the rock record. When the ice melted, the accumulated CO2 dissolved in seawater, forming carbonic acid. This acid rain weathered rocks aggressively, washing enormous quantities of calcium into the oceans. The calcium combined with carbonate to form thick layers of limestone deposited directly on top of glacial debris. These cap carbonates appear on every continent. Same structure, same composition, same position atop glacial deposits. They're the calling card of Snowball Earth episodes, proof that the planet can freeze completely and then thaw with equal extremity. What allowed life to persist through these frozen eons? Probably the same refugia that might sustain it through future climate catastrophes. Volcanic regions where heat keeps ice at bay. Deep ocean vents where chemosynthetic organisms thrive independent of sunlight. Thin spots in sea ice where enough light penetrates for photosynthesis. Studies of modern Antarctic ice lakes show cyanobacteria creating tiny oxygenated zones even beneath meters of ice. Just a millimeter or 2 of oxygen-rich water, but enough to sustain metabolism. If similar processes operated during Snowball Earth events, they could have preserved the genetic diversity that exploded after the ice retreated. And explode it did. The Ediacaran fauna appeared shortly after the last Snowball episode. Strange, soft-bodied organisms unlike anything before or since. Then came the Cambrian explosion, when virtually all modern animal body plans emerged within a few million years. Was this diversification triggered by the glaciations? The genetic bottlenecks might have created evolutionary pressure. The nutrient-rich sediments eroded by glaciers could have fertilized the oceans. The surge in calcium availability from weathering during the thaw enabled organisms to build shells and skeletons for the first time. Catastrophe and innovation intertwined, the worst climate events in Earth's history potentially setting the stage for the complexity that followed. These ancient ice ages operated on timescales so vast they seem disconnected from human concerns. 70 million years, 50 million years. These durations exceed our capacity for intuitive understanding. Yet they demonstrate the climate system's potential for extreme, prolonged state changes. They show that Earth can settle into configurations radically different from present conditions and remain there for geological ages. They prove that feedback mechanisms can lock the planet into states that persist until some external forcing strong enough to overcome them appears. The triggers for these ancient glaciations weren't mysterious. The Huronian freeze resulted from atmospheric chemistry changes. The Cryogenian events coincided with continental configurations that maximized weathering and minimized volcanic CO2 emissions. Plate tectonics positioned continents near the equator, where weathering is most intense. A volcanic province in what's now Canada eroded rapidly, consuming atmospheric CO2. Volcanic activity hit historic lows. CO2 levels dropped below 200 parts per million, less than half present concentrations. Once that threshold was crossed, ice albedo feedback took over. Ice reflects sunlight. More ice means more reflection. More reflection means cooler temperatures. Cooler temperatures mean more ice. The feedback became self-sustaining. Ice advanced from the poles toward the equator, reflecting more sunlight with each degree of latitude it covered. By the time glaciers reached the tropics, the planet reflected most incoming solar radiation back to space. average global temperature fell to -50°C. Even the equator froze solid. Breaking out of that state required extraordinary forcing. Only the gradual accumulation of volcanic CO2 over millions of years provided enough greenhouse warming to reverse the freeze. Once CO2 concentrations climbed high enough, perhaps 300 times present levels, the ice began melting. And once melting started, albedo feedback ran in reverse. Less ice meant less reflection. Less reflection meant warmer temperatures. Warmer temperatures melted more ice. The transition from snowball to hothouse was faster than the freeze. Positive feedbacks work both ways. What does this mean for current climate change? We're not going to trigger a snowball Earth. We're pushing the system in the opposite direction toward warming. But the fundamental lesson applies. Feedback mechanisms can amplify forcing, creating changes far larger than the initial perturbation. We've increased atmospheric CO2 by about 50%. That alone would warm the planet by roughly 1 degree Celsius if everything else remained constant. But everything else doesn't remain constant. Warming melts ice, reducing albedo. It increases water vapor, a greenhouse gas. It thaws permafrost, releasing methane and CO2. It weakens ocean circulation, altering heat distribution. It changes cloud patterns, affecting both reflection and heat trapping. These feedbacks amplify the initial warming. 1 degree becomes 2, 2 becomes 3. Each increment activates additional processes that further alter the energy balance. The ice ages teach us that Earth's climate system is sensitive. Small changes in forcing can produce large changes in state, especially when feedbacks align. They also teach us that these changes can persist far longer than the forcing that triggered them. The Milankovitch cycles that paced recent glaciations involve variations in Earth's orbit and axial tilt. These changes alter the distribution of solar radiation by just a few %, yet they're enough to tip the planet into or out of ice ages that last tens of thousands of years. Why do small orbital changes produce such large climate responses? Feedbacks. Ice sheets grow and shrink. CO2 levels rise and fall. Ocean circulation reorganizes. Vegetation patterns shift. Each of these processes feeds back on temperature, amplifying the orbital signal. Current forcing from greenhouse gases is far larger than the orbital variations that control glacial cycles. We've increased radiative forcing by roughly 2 watts per square meter, an amount that exceeds the maximum difference between glacial and interglacial conditions. And we're applying this forcing faster than anything in the ice core record. The system is responding. Ice is melting. Oceans are warming. Precipitation patterns are shifting. But the full response is still developing. There's warming already locked in that hasn't yet manifested. There are feedbacks already triggered that will continue amplifying change for decades. This is what makes delay so dangerous. Every year of continued emissions adds to the committed warming. Every 1/10 of a degree makes the eventual stabilization harder to achieve. Every delayed action increases the magnitude of change we're committing future generations to endure. The ice ages also reveal that climate change isn't smooth. It happens in jumps. The Younger Dryas cold snap interrupted deglaciation with remarkable speed. Temperatures in Greenland dropped 10 degrees Celsius in a decade. They remained depressed for over 1,000 years, then jumped back up almost as quickly. What caused these abrupt shifts? Probably changes in ocean circulation. Meltwater from retreating ice sheets altered the salinity of the North Atlantic, weakening the circulation that brings warm water northward. When circulation weakened, the northern hemisphere cooled. When it resumed, warming returned. These aren't theoretical concerns. Ocean circulation is already showing signs of weakening. The Atlantic meridional overturning circulation has slowed by roughly 15% since the mid-20th century. Models suggest further weakening as meltwater from Greenland continues increasing. If circulation shuts down completely, the consequences would be severe. Regional cooling in the North Atlantic and Europe, disruption of monsoon systems, reorganization of precipitation patterns globally, and potentially triggering of additional feedbacks that amplify the instability. We're conducting an experiment on the only planet we have. The ice ages show us the magnitude of changes possible, the speed at which transitions can occur, the persistence of altered states once established, the difficulty of reversing course once thresholds are crossed. The paleoclimate record doesn't just warn us about future warming, it reveals something equally unsettling: the possibility of abrupt, irreversible collapse. Not gradual decline, but sudden reorganization. State changes that occur faster than societies can adapt. Consider the Greenland ice cores. They document dozens of abrupt climate shifts during the last glacial period. Temperature swings of 10 to 15 degrees Celsius occurring over just a few decades, sometimes faster. The Younger Dryas transition happened in less than 10 years. 1 decade of normal variability, then a completely different climate state. These weren't small regional fluctuations. They were hemispheric reorganizations driven by changes in ocean circulation, atmospheric chemistry, and ice sheet dynamics. Once triggered, they cascaded through the climate system faster than any linear model predicted. We're approaching similar thresholds now. The Greenland ice sheet is losing mass at accelerating rates. Summer melt now penetrates deeper into the interior. Surface lakes form, drain through cracks, and lubricate the base of the ice sheet, accelerating flow toward the ocean. This isn't a process that reverses easily. Once ice sheets start collapsing, the physics favor continued collapse. Thinner ice absorbs more heat. Lower elevation means warmer temperatures. Meltwater darkens the surface, reducing reflectivity. Each consequence amplifies the initial change. The Antarctic ice shelves tell a similar story. These floating platforms of ice buttress the glaciers behind them. When they collapse, inland ice accelerates toward the sea. The Larsen B ice shelf disintegrated in just 6 weeks during 2002. It had been stable for over 10,000 years. Then it was gone. What triggered the collapse? Surface meltwater, pooling in cracks. When enough water accumulated, it wedged the ice apart through a process called hydrofracturing. The entire shelf shattered like glass. The glaciers that Larsen B had been holding back immediately accelerated. Some increased their flow rate by 8 times within months. They're still flowing faster today, 2 decades later. The collapse was irreversible on human timescales. This pattern appears throughout the paleoclimate record. Systems exist in stable states until forcing pushes them past a threshold. Then they transition rapidly to a new stable state. The transition itself is fast. The new state persists. The Atlantic meridional overturning circulation shows warning signs of approaching such a threshold. This ocean current system transports enormous amounts of heat northward, moderating climate across Europe and North America. Paleoclimate evidence shows it has shut down before, triggered by freshwater influx from melting ice sheets. When circulation weakens or collapses, regional cooling follows. Not global cooling, but dramatic temperature drops in specific regions, even as the planet overall continues warming. Europe could experience winters 20 degrees colder while the tropics bake. Monsoon systems could fail. Agricultural zones could shift hundreds of kilometers in a single decade. Models suggest we're already 1/3 of the way toward the threshold for circulation collapse. Some estimates indicate we could cross it within this century if meltwater from Greenland continues accelerating. Once crossed, the circulation might not restart for thousands of years, even if we removed all excess CO2 from the atmosphere. This is what makes certain climate changes effectively irreversible. Not because the physics prevents reversal, but because the timescales for natural recovery exceed anything relevant to human civilization. A collapsed ice sheet might eventually regrow, but only over tens of thousands of years. A shutdown ocean circulation might restart, but only after millennia of adjustment. We're making decisions now that commit the planet to states we cannot undo. Each increment of warming increases the probability of crossing thresholds we haven't identified yet. Each year of delay reduces our ability to prevent the most dangerous transitions. The ice ages also reveal the astonishing extent of change possible within Earth's climate system. During the Cryogenian period, between 720 and 635 million years ago, the planet may have experienced snowball Earth events, global glaciation, ice extending from poles to equator. The evidence comes from glacial deposits found at tropical latitudes. Rocks that formed near the equator contain unmistakable signs of glaciation. Dropstones, tillites, and striated bedrock. Magnetic minerals in these rocks preserve the orientation of Earth's magnetic field at the time of deposition, confirming their equatorial origin. How does a planet freeze completely? Through runaway ice albedo feedback. Once ice covers enough surface area, it reflects so much sunlight that temperatures drop further, more ice forms, reflectivity increases, cooling accelerates. Eventually, ice reaches the tropics. At that point, Earth reflects over 60% of incoming solar radiation. The planet becomes a frozen ball, with global average temperatures plummeting to -50 degrees Celsius. Life survived somehow, probably in refugia near hydrothermal vents, under thin ice in equatorial regions where sunlight still penetrated, or in pockets of liquid water around volcanic activity. But the biosphere was severely stressed. When the ice finally melted, triggered by millions of years of volcanic CO2 accumulation, the planet swung violently in the opposite direction. Cap carbonates deposited immediately after snowball Earth events record this transition. These distinctive limestone layers formed when CO2-rich rainwater weathered the exposed rock surfaces, washing massive amounts of dissolved minerals into the oceans. The chemistry suggests atmospheric CO2 levels during deglaciation reached hundreds of times higher than present values. Earth went from frozen to greenhouse in geologically rapid succession. The Huronian glaciation represents an even longer ice age, lasting around 70 million years between 2.4 and 2.1 billion years ago. This glaciation coincided with the Great Oxygenation event, when photosynthetic organisms first began producing oxygen in significant quantities. Before oxygenation, Earth's atmosphere contained substantial methane, a powerful greenhouse gas produced by anaerobic microbes. When oxygen appeared, it reacted with methane, forming carbon dioxide and water. Both are weaker greenhouse gases than methane. The atmospheric heat-trapping capacity collapsed. Global temperatures plummeted. Ice expanded from the poles. This wasn't just climate change. It was an extinction event. The rise of oxygen poisoned most of the existing biosphere, which had evolved in an oxygen-free world. Organisms that couldn't tolerate oxidative stress died out. The anaerobic microbial mats that had dominated Earth's surface for billions of years were decimated. Only organisms capable of oxygen respiration survived and eventually thrived. This catastrophic transition fundamentally restructured the biosphere, setting the stage for all subsequent evolution. Without the Huronian glaciation and the extinction it caused, complex life as we know it might never have emerged. These ancient ice ages demonstrate that Earth's climate can occupy states radically different from anything human civilization has experienced. They also show that transitions between states can be triggered by changes in atmospheric composition. The composition changes we're causing now are happening orders of magnitude faster than the Great Oxygenation event. We're increasing atmospheric CO2 concentrations at a rate unprecedented in the geological record. Not just faster than any natural change during human history, but faster than almost anything in the entire paleoclimate archive. The Paleocene-Eocene thermal maximum, one of the most rapid warming events in deep time, saw temperatures rise by 5 to 8 degrees over several thousand years. We're on track to match that warming in less than 2 centuries. The biosphere hasn't faced this rate of change since the asteroid impact that ended the Cretaceous period. Species cannot adapt or migrate fast enough. Ecosystems cannot reorganize. We're conducting an experiment in evolutionary stress testing, and the results won't be favorable. Coral reefs are collapsing globally, not slowly declining, but experiencing mass bleaching events that kill entire reef systems within months. These ecosystems evolved over millions of years. They're being destroyed in decades. Once they're gone, they won't recover on any timescale relevant to human society. The biodiversity they support will be permanently lost. Arctic ecosystems face similar collapse. Permafrost that has been frozen for tens of thousands of years is thawing. The organic material it contains is decomposing, releasing methane and CO2. This creates another feedback. Warming thaws permafrost, releasing greenhouse gases, causing more warming, thawing more permafrost. Current estimates suggest permafrost thaw could release as much carbon as all human emissions from fossil fuels over the next century. That's not additional warming we're causing directly. That's warming the Earth system will cause itself, triggered by the warming we've already initiated. This is what makes climate change so dangerous. We're not just adding heat to a passive system. We're activating processes that generate additional heat independent of our future choices. The ice ages show us what happens when these feedbacks align. Small initial changes trigger large responses. Those responses activate additional processes. The system transitions to a new state and remains there until some external forcing pushes it back. We're pushing hard in the direction of warmth. The system is responding. Ice is melting. Permafrost is thawing. Ocean circulation is weakening. Each response activates feedbacks that amplify the change. The question isn't whether we'll alter Earth's climate. We already have. The question is how far we'll push before we stop. How many feedbacks will trigger? How many thresholds will cross? How different will make the planet from the stable Holocene climate that allowed civilization to flourish? Every fraction of a degree matters, not metaphorically, literally. Each increment of warming increases the probability of triggering irreversible changes. Half a degree determines whether coral reefs survive or collapse. 1 degree determines whether Arctic permafrost remains frozen or thaws. 2 degrees determines whether Greenland's ice sheet slowly declines or rapidly disintegrates. We're currently on track for somewhere between 2 and 3 degrees of warming by 2100. That's the optimistic scenario, assuming we implement every climate commitment currently on the table. The pessimistic scenario, if emissions continue growing, reaches 4 or 5 degrees. 5 degrees doesn't sound like much. It's a cool autumn morning versus a warm spring afternoon. But that's local weather. Global average temperature change of 5 degrees represents a completely different climate state. The last time Earth was 5 degrees warmer than pre-industrial levels, sea level was 25 meters higher. There were no permanent ice sheets. Forests grew in Antarctica. That world took thousands of years to develop. We're creating the forcing for it in 2 centuries. The lag between forcing and full response means we're committing to changes we won't see for generations. But they're coming. The physics is unavoidable. The ice ages teach us humility. They show us that Earth's climate is powerful, dynamic, and capable of changes that dwarf human experience. They demonstrate that stable climate is the exception, not the rule. That transitions can be abrupt. That thresholds exist. That once crossed, there's no easy path back. We're testing the boundaries of a system we barely understand. The paleoclimate record is our only guide to how that system behaves under stress, and every page of that record warns us. Slowly building forcing, sudden response, long-lasting consequences. The ice isn't just frozen water, It's a record, a warning, a mirror held up to our current trajectory. When you look at an ice core, you're looking at atmosphere from another world. When you study its chemistry, you're reading the biography of a different Earth. That Earth survived its ice ages. Life persisted. The planet continued. But the species that dominated before the transitions weren't always the ones that dominated after. The world that emerged from each glacial period was fundamentally different from the world that entered it. We're creating the next chapter in that story. Whether it will be readable by our descendants depends entirely on what we do next. The ice remembers everything. Every frozen breath of ancient atmosphere. Every shift in temperature. Every threshold crossed. And right now, it's melting faster than at any point in the past 12,000 years. We've spent this journey traveling through deep time. 70 million years of Huronian ice. 50 million years of cryogenian freeze. The slow oscillations of the Quaternary. Each episode teaching the same brutal lesson. Earth's climate doesn't negotiate. It responds to physics, energy balance, atmospheric composition, feedback loops that amplify change beyond the initial trigger. Here's what separates us from every previous climate transition. Speed. The Great Oxygenation Event took millions of years to transform the atmosphere and trigger the Huronian glaciation. We've altered atmospheric chemistry by a comparable amount in 2 centuries. The Milankovitch cycles that paced recent ice ages shifted solar forcing by fractions of a percent over thousands of years. We've increased radiative forcing by magnitudes larger in decades. The system is trying to respond. Greenland loses 280 billion tons of ice annually. Antarctica sheds 150 billion tons. These aren't abstract numbers. They're momentum. Every ton of melt raises sea level, reduces albedo, adds fresh water to ocean circulation systems already showing signs of weakening. The feedbacks we've studied throughout the ice ages, the ones that turned small changes into massive reorganizations, are activating now. But there's a difference this time. Previous climate changes happened to a planet without cities, without agriculture dependent on specific rainfall patterns, without infrastructure designed for stable sea levels. The Younger Dryas plunged temperatures by 10 degrees in a decade, and life adapted because ecosystems weren't already fragmented by development. Species could migrate, populations could shift. We've eliminated most of that buffer. We've built civilization in a narrow climate envelope. We've optimized for efficiency under stable conditions. We've created systems that work brilliantly when nothing changes and fail catastrophically when everything does. The ice ages also taught us about commitment. Once certain thresholds are crossed, reversal becomes extraordinarily difficult. Ocean heat content will continue rising for decades, even if emissions stop tomorrow. Ice sheets will keep shrinking for centuries. The CO2 we've emitted will influence climate for thousands of years. Some fraction persists for 10,000 years or more. This permanence is what the paleoclimate record makes unavoidable. We're not just altering weather patterns for our generation. We're reshaping the planetary boundary conditions for timescales that exceed recorded history. The choices we make now will determine climate states for longer than agriculture has existed. Every ice age eventually ended. The Huronian thawed when volcanic CO2 accumulated for millions of years. The cryogenian snowballs melted under greenhouse conditions hundreds of times stronger than today. The Quaternary glacials retreated when orbital parameters favored warming, and CO2 levels rose by 80 parts per million over 10,000 years. We've increased CO2 by 140 parts per million in 200 years. We've applied forcing that rivals the transitions that ended ice ages, except we're pushing toward heat instead of cold. And unlike those natural transitions, which unfolded over millennia, we're compressing the change into timescales measured in human lifetimes. The question isn't whether Earth's climate can handle this. The planet has survived snowball episodes, hothouse periods, and everything between. The question is whether human civilization can handle it, whether our infrastructure, agriculture, and social systems can adapt to changes happening faster than anything in the ice core record. The Paleoclimate Archive is unambiguous. Rapid forcing produces rapid response. Feedbacks amplify initial changes. Thresholds exist where systems transition from one stable state to another. Once crossed, these transitions can be irreversible on human timescales. We're approaching several such thresholds simultaneously. Ice sheet collapse, ocean circulation shut down, permafrost carbon release. Each represents a point of no return. Not metaphorically, physically. Cross them, and the climate system commits to changes we cannot prevent through any technology we currently possess. This is what makes the next few decades so critical. Not the next few centuries. The next few decades. The warming already locked in will continue regardless of our actions. But how much additional warming we commit to depends entirely on choices we make before 2050. Every year of delay narrows our options. Every fraction of a degree makes stabilization harder. The ice ages show us that Earth's climate has multiple equilibrium states. Glacial periods that lasted 90,000 years. Interglacials that lasted 10,000. Snowball episodes that persisted for tens of millions of years. The planet can settle into any of these configurations and remain there until forcing strong enough to overcome the feedbacks appears. We're creating that forcing now. We're pushing the system toward a state it hasn't occupied in millions of years. A world warmer than any interglacial of the Quaternary. Warmer than the Pliocene, when sea levels were 15 to 25 meters higher. Potentially warmer than the early Eocene, when crocodiles swam in Arctic waters. Those aren't brief excursions. They were stable climate states that persisted for millions of years. The planet adjusted to them. Ice sheets retreated or vanished entirely. Ocean circulation reorganized. Ecosystems migrated to new latitudes. The Earth system found equilibrium and remained there. We're not aiming for those climates deliberately, but we're applying the forcing that could take us there. The only question is whether we stop before we cross enough thresholds to commit ourselves to those outcomes. The Huronian glaciation killed most of Earth's biosphere and fundamentally restructured what remained. The cryogenian snowballs nearly extinguished complex life entirely. The Quaternary ice ages forced human ancestors into refugia, small pockets of habitability in a world dominated by ice. Each transition came with extinction. Each reorganization eliminated species that couldn't adapt fast enough. We're creating the conditions for another such transition. Not toward ice this time, toward heat. And we're doing it faster than anything in the geological record, except asteroid impacts. The ice cores from Antarctica and Greenland contain 800,000 years of climate history. Every layer, every trapped bubble, every isotope ratio tells the same story. Small changes in forcing produce large changes in climate when feedbacks align. The system is sensitive. The transitions are often abrupt. The consequences persist far longer than the forcing that triggered them. We've known this for decades. The science isn't new. The warnings aren't recent. What's new is the acceleration. The rate at which we're approaching thresholds. The narrowing window for action before committed warming makes certain outcomes unavoidable. The paleoclimate record offers no comfort. It shows us what's possible when climate systems destabilize. Ice sheets that collapsed in centuries. Ocean circulation that shut down in decades. Temperature swings that reorganized entire hemispheres within human lifetimes. These aren't theoretical scenarios. They're documented events that happened repeatedly throughout Earth's history. The difference is that those events occurred in worlds without 8 billion people. Without global infrastructure, without agricultural systems feeding populations dependent on specific climate patterns. We're running the same experiment in a world with far less capacity to absorb the shock. Stand on the shore of Lake Huron, where the Huronian glaciation was first discovered. Look at the rocks. They've been there for 2.4 billion years, recording the longest ice age in Earth's history. They survived that freeze. They'll survive whatever comes next. The question is whether we will. The ice ages didn't end because Earth decided to be merciful. They ended because forcing changed. Volcanic CO2 accumulated, orbital parameters shifted, ocean circulation reorganized, the physics demanded it, and the climate responded. There was no choice involved, no negotiation, just cause and effect operating on planetary scales. We're now the cause. The effects are developing around us. Ice melting, oceans warming, weather patterns reorganizing, each change activating feedbacks that ensure more change is coming. The system we've set in motion will continue operating according to physical laws that don't care about economics, politics, or whether we think the pace of change is fair. The ice remembers. It remembers when the planet froze for 70 million years, when it thawed into hothouse conditions, when it oscillated between glacial and interglacial states for millions of years. It remembers every threshold crossed, every feedback triggered, every reorganization forced by changes in atmospheric chemistry, and right now, it's melting, not slowly, not gradually, faster than any time in the Holocene, faster than during most of the last deglaciation. We're watching the beginning of something the ice has recorded before, a climate transition driven by atmospheric change. Only this time, the change is us. The forcing is ours. The consequences will be too. The geological record makes one thing absolutely clear. Climate change isn't a problem we can solve later. It's a threshold we're approaching now. Every year we wait, every increment of additional forcing, every feedback we trigger makes the eventual transition more severe and the new equilibrium state more different from anything civilization has experienced. The ice ages survived. The planet continued. Life persisted, though often in forms dramatically different from what existed before. That will happen again regardless of what we do. Earth's climate will eventually stabilize in some new configuration. The oceans will reach equilibrium. Ice sheets will find their appropriate size. Ecosystems will reorganize. But that process takes millennia, and the world that emerges won't necessarily be one that supports 8 billion humans living in the narrow climate band we've built everything around. The rocks don't care. The ice doesn't care. The climate system responds to physics, and physics is indifferent to human timescales. We're the first species capable of altering planetary climate through our own activity. We're also the first species capable of understanding what we're doing and choosing a different path. That makes this moment unique in Earth's 4.5 billion year history. Not because the climate is changing, it's always changed, but because for the first time, the change is being driven by organisms that can comprehend the consequences and still have time to alter the trajectory. The ice ages show us what's possible, what's happened before, what the climate system is capable of when pushed beyond its equilibrium. They're not predictions, they're demonstrations, proof of concept for planetary reorganization, evidence that the stable climate we've built civilization around is neither permanent nor guaranteed. The next chapter in Earth's climate story is being written now, not in geological time, not over millions of years, in decades, by us. The ice will record it, layer by layer, bubble by bubble, preserving our choices for future scientists to study, if any remain to do so. And those future observers will see in the chemistry what we're seeing in the physics, a species that understood the consequences, possessed the tools to prevent catastrophe, and chose how to respond in the brief window when response was still possible. The longest ice age lasted 70 million years. The shortest interglacials, barely 10,000. Earth's climate exists in states we've never experienced and operates on timescales we struggle to comprehend. But the fundamental rules remain constant. Forcing produces response. Feedbacks amplify change. Thresholds, once crossed, commit the system to transitions that unfold according to physics, not preference. We're conducting the experiment. The results are developing. And unlike the ice sheets that advanced and retreated according to orbital mechanics, unlike the atmospheric transformations that took millions of years, unlike every previous climate transition in Earth's history, this one is happening on a timescale where we can still influence the outcome. That window is closing, the ice is melting, the feedbacks are activating, the thresholds are approaching. What happens next isn't written in the geological record. It's being determined by what we do right now.